So welcome back, everybody. Hope you're doing fine. So the schedule today, we are trying to keep this kind of the first 20 minutes where we do some theory and also discuss perhaps some things related to the exercises. And as you can see from the program which we have set up here, we will continue with some of these discussions on the exercises in the beginning now. And then I wanted to get into the next topic, which is actually the real first topic which we start with. And that's the work energy theorem. And that has some very important consequences for us. We will study things like energy conservation. We are going to look at the implications for the type of forces which are relevant for the work energy theorem. So there are many, many important small aspects here. And we're going to start to scratch the surface so that in case during the weekend, you really feel that you want to study classical mechanics, there are some topics here you can dive into and take a look at chapters 4.1 and 4.2 in Taylor's textbook, because this is where we will start again on Monday. So this is just a kind of way to motivate for what is going to come now. But first, I want to give you some quick messages. So we will have breakout rooms for those of you who are online. And again, like last Friday, George and Julie will be in the breakout rooms. So feel free to join them. We are going to open them up when we just start with the exercise session. And then I will just float around in the hall here. The other thing, Julie told me that, the feedback on the first homework set is going to be available during the weekend. So typically we try to give you feedback roughly 1 week after the deadline. That's the kind of schedule we are aiming at. Sometimes we may be earlier and sometimes we may be a little bit later. Hopefully this is something we can live with all of us. So the thing I wanted to do now is just look quickly at the basic philosophy of the exercises 4, 5, and 6 in the homework. And the basic philosophy, if you want to just state it in just one sentence, it's about objects falling or moving under simple forces. And these are cases which we can normally integrate up easily and find the velocity and the position given the acceleration when we have analyzed the problem. And what's the issue in these exercises is simply to figure out in which direction the forces are acting and set up a coordinate system and then set up the forces. Like we did when we looked at exercise 5 on Wednesday. Exercise 4 of a golf ball is actually pretty similar to that one. But let me quickly remind you of some of the basic things which we are doing in these exercises so that we keep this at a slightly more overarching level. So if you look at exercise 4, which we didn't do on Wednesday, so the thing which we need to do is obviously to find a reference frame. That's one of the first things we do. And the reference frame, which is reasonable according to the type of problem we are looking after. Sometimes you may have to tweak the reference frame in order to simplify the equations. So typically here, you would choose something like the y, a Cartesian coordinate, an x, y, and z. And depending on whether this is an object which is moving upwards or downwards, you may define negative directions according to the type of problem which you have. And you would often then have, if you have a Cartesian system, which is often the simplest one, and the one you will see again and again, we will then choose unit vectors in these directions. So we have an I, there is a j here, and then there is a k vector. And we know that these vectors are all orthogonal. So when we take the dot product, this is equal to I times k, which is also equal to j times k, and they're all equal to 0. And then we know that the absolute values of these unit vectors, when we write them like this, they're just equal to 1. Now, in this exercise, so I'm not going to give you the whole answers because we want you to think about the forces. So you have in a way to set up the forces in the, or the acceleration in the X, Y, and Z direction. But when you've done that, then you typically have some initial conditions which you can plug in. So in this typical exercise, what you would have then is an initial velocity. And since we have a movement in the three directions, in our case, we would have a velocity which is now given by v of t equals 0, which we typically write as a v0 like this. And that would have something like a velocity in the y direction, in the x direction, and the z direction. So in this specific case, what we have is something which goes like v0 times a cosine theta. There is an I vector, and then there is nothing in the y direction. And then we have plus some constant v0 times sine theta multiplied with k. So these are the initial conditions, and we would often write this if we want to use a more compact vector form. We would typically write it like this. So there's an angle theta. This v0 is just a constant, and then we have the cosine and the sine. So this is us setting up the initial conditions. And then we know that since this is an object which is under the influence, so it has an initial velocity, that's what we give the system. And then the rest is done by the gravitational force. So that means that if we now pick the z direction as the one which the gravitational force is acting along, then we can use that one to find the velocity as a function of time. If we integrate up, like we did in the very beginning, when you had just an object falling in one dimension under the gravitational force, then we found that the velocity in that direction was given by minus g times t plus some initial velocity, right? So it means that if we now look at the velocity here, if we now integrate up, it means that the velocity in the x direction, in the z direction, which we're going to call vz of t, that is going to be given by a v0 of sine theta, and there's going to be a minus g times t when we chose the initial time to be equal to 0 seconds. And then when you have these quantities, the next thing you need to do is to integrate and get the positions in the x, y, and z directions. So that means that when we look at x now, so I'm taking away the vector signs. So we have x of t is going to be given by an x0, and then we're going to have an integral of from 0 up to time t, and then we have the velocity in the x direction as a function of time of dt. Now the velocity in the x direction, there is no gravitational force acting on it, so that is just constant, right? So that means that if we take that quantity, when we integrate it up, then x of t is now going to be given by this x0, which I haven't specified here, plus some v0 of cosine theta times time. Now, in the y direction, for this specific case, there is no force. So that means nothing happens there. It's pretty boring. So that means you don't move in the y direction. So y stays equal to 0. I hope that agrees with what you guys have found as well, right? So that means that y of t is just simply equal to y0, which we put equal to 0. And then finally, the thing which we need is to find the position in the z direction. So c of t is going to be equal to v0, which is the initial one when we integrate up sinus theta times t, and we're going to have a minus g times t squared divided by 2 here. So the velocity went like v0 sine theta minus g times t, and then we integrate up again time, and we get minus half gt squared. And then this will be the position as a function of time. And then you can ask yourself, when does it reach the ground? So that is when this object comes to rest. So you would typically then say, when does it hit the ground? Does it hit the ground? And that's clearly when z of a final time is equal to 0. So that means that the only thing we need to do now is just to plug in the equations here. Sine theta times this final time minus g times t squared final time divided by 2. And then we can reorder and we find the final time, which would now be Tf equal 2 times V0 of sine theta and divided by g. So now we found the time when this object comes to rest. And then you could ask yourself, how much did it travel in the x direction? Because we know the final time when it comes to rest. So it started at some x0, y0, z0. And now we are asking ourselves, how far did it travel in the x direction? So if you now ask that question, then we know that this is x of t of f. And then we simply go back to the expression we had, and we started at 0. So we put x0 equal to 0. And then the only thing we need to plug in is this equation for V0 cosine theta times t. So that means that I get V0 times cosine theta times this TF. And now I can plug in TF because I know TF, which I have here. So that means I can now get is equal to 2 times V0 squared. And then I have a sine theta, cosine theta divided by g. And then we know that the quantity which you have here with 2 and multiplied with sine theta, we can simplify that with one of the famous trigonometric relations. So we can write this as a V0 times a sine 2 theta divided by g. So this kind of, I didn't give you all the details because I want you obviously to analyze the problem and spell out the forces. When you have found the forces, it's just a matter of integrating up the equations, and then you have the answers. And then clearly you have questions like, when does it come to rest? How long did it travel in a specific direction? And when you have these quantities as a function of time, you know exactly how you can solve these type of problems. Essentially, although these kind of problems may sound a little bit boring, what we want to have you with us is actually the way of thinking. You analyze a problem, you find the forces, you find the acceleration, and then you integrate up and you find the dynamics of the system, which essentially means finding the velocity and position as a function of time. And in a certain sense, the rest of the course is actually going to rotate around these kind of principles, but we are going to look at a little bit more complicated problems, because else, I mean, this course would become pretty boring. Okay, so what I want to do now, unless you have any questions about these exercises. So exercise 4, 5, and 6, they're pretty similar. And in exercise 6, you actually do it numerically. And the challenge there is if you want to use this kind of more compact notation for vectors in 2 and 3 dimensions in Python. Any questions so far? I can see many people nodding, so I guess most of you think this is pretty okay. So what I want to do now is to bring up the topic in the last few minutes here, the topic which we are going to deal with next week and the week thereafter, which is going to lead to very important laws, which are called conservation laws. And with these laws, we can actually, without having done a calculation, we can say something about how the system will behave. So one of the first things here is actually what we call the work energy theorem. And you've probably seen this when you took physics 181, for those of you who've been at Michigan State all the time. This is a very important theorem. And in a sense, this is, it's gonna prepare us for understanding conservation of energy and say something about the forces. So we're going to meet forces which we call conservative forces, and they essentially conserve important quantities. So that means that when something is conserved, it doesn't change over time. That's a very important property. And we have forces which don't conserve energy, which dissipate energy, for instance. Then we have to deal with other types of normally equations. But when we have a conservative force, as we will see, we can actually use that to find the velocity without thinking of time. So till now, what you have seen is us setting up the equations of motions, and then we integrate. So the question is, there may be cases where we cannot do the integration, or it's not fully feasible. Then the work energy theorem can allow us to find things like the velocity and the position in a different way. So it's an alternative way to find quantities like the velocity and the velocity, in particular the velocity of a system, and also the acceleration. So let's take first a small look at the basic things. So in a way, what we're doing now is to try to catch many birds with just one stone. Actually a violent statement, isn't it? To catch many birds with just one stone. In the Scandinavian languages and in German, it's just to catch 2 flies with 1 hit, which is perhaps less violent. In Italian, it's pretty funny. In Italian, it's to catch 2 pigeons with 1 bean. I don't know how you can do that. So it's more the fact that you want to show that things are impossible to do, right? But here, we're actually going to catch many birds with just 1 stone. Okay. So the thing which we start with is, as we have done before, we have assumed that we have a force which acts on the system. Let me just do that. So we have a force, and this force has normally been assumed to be a quantity. So we're putting arrows here, a quantity which depends on position, it depends on velocity, which also depends on time. The position depends on time, and then we have time. So what we now are going to do is to look at a slightly different case. But before we do that, we are going to set up the kinetic energy. So we define the kinetic energy, and I'm going to use this letter K, and we define kinetic energy. So this K is given by 1/2 times the mass of the object times V squared. And when we look at the dimensions, we see why this dimension is correct. And now there's a force acting on the system. But let's now look at the small change in kinetic energy. So we're assuming now that we have a kinetic energy which varies over time. So we look at the instantaneous change in kinetic energy. And we know that this has to equal 1/2, and then we have the mass. And the only quantity which now we assume is time dependent is velocity. So we are making an assumption, this is an important assumption we are making, that the mass is not time dependent. So the object doesn't lose mass. If it loses mass, then we have to be careful with what we are doing now. But what we have now is V times V. So this is actually the value of the velocity. So it's a dot product we're taking. And now you see that what we did in homework number 1, even if it was a set of boring exercises with vector products and the associative properties of vector multiplications and so on, you see now that we can use homework 1 and exercise 3. So if you go back to what you did then, we will need that when we take the derivative. So if you go back to homework 1 in exercise 3, then we know that this is something we can rewrite as 1/2 times m. And then we have a dv with respect to t of v plus, and then we have a v dv dt. But since these are the same quantities, we can then rewrite this as m. We get rid of the factor over 1/2, and then we have dv dt multiplied with v. Now, there's an interesting thing. If you now observe the first term which you have here, if you look at this term here, what is this actually equal to? If you now spool back a little bit to what you may have seen before, the force. Excellent. So the This is something we can now rewrite as the force multiplied with the velocity. But we know that the velocity is actually equal to the derivative of position with respect to time. So this is actually quite an interesting quantity which we have here. Now, the thing we are going to do now is to discretize. And when we discretize, I'm just going to use some 1 to 2 more minutes, and then we're going to look at exercises. So we're going to let this d of k, we go over to a finite quantity, a delta k. So it's not an instantaneous value anymore. We let time become a discrete in terms of discrete time steps. And then we look at the finite displacement of delta r. Then I'm going to rewrite the equations, because we know that if I take the limit of delta t goes to 0 of delta k with delta t, this is the same as the instantaneous change in kinetic energy. Now, what we have now is something which is given by delta k divided by delta t, which is equal to the force acting on delta r divided by delta t. We take away delta t, and then we are simply left in a change in kinetic energy, which is given by the force multiplied with a displacement. So we define then the change in energy as the work which is done. So this is a definition. So work done by the force during a displacement So we move an object, we apply a force to it, and that's going to be given by the change in kinetic energy. So we have a displacement delta R here. Now then, what you could think of is the following. So you could now think of a series of such small displacements. So you do a small displacement here, a delta R1, you have a new one, you have a delta R2, and then you have a delta R3, etc., up till you reach a final displacement here, delta R of n. So you could now think of moving this quantity over a certain distance, and you do all these kind of small displacements. So it means that then the delta K is then something you can write as a force. And then we can now think of a force which acts on a small displacement of a delta Ri. So at every one of these, there is an associated force. And you see that the product of these two vectors is a scalar. So this goes all the way up to some f of n. In general now, what we end up doing is to assume that this is equal to the kinetic energy at the end point. So we call this the kinetic energy at n squared minus the kinetic energy at an initial time, which we now just can call V1. So this delta K represents the difference in kinetic energy. The next thing we do, we discretized, and now we take the limit where these changes are becoming infinitely small. And we define this quantity as the work which is done. So work done, and we just put a W here. And this is something which you probably have seen before. What we are going to do now is to define, when we now take the discretize, so the work energy theorem, if we now set up a continuous change in this delta R, so we let this delta R go over to a dt, and then we can integrate up the quantity which we have here. So the work energy theorem says that us going from 1 to n is something which we would write like a C, which is now the path we are taking with a force, which depends on R, V times T, but now multiplied with D of R. So this is where I'm going to stop today. But I want you to think a little bit about the consequences of what you have here. So if you can find this integral, you know now that you would have an initial velocity. So typically, the typical situation is that you know this initial velocity. And when you integrate up, you can find the final velocity. So that's the whole point. So instead of integrating up the equations starting with the acceleration and getting velocity and position, we can now use the work energy theorem with an initial velocity. And if we can integrate up the quantity which you see here, this quantity here, you can then, when you integrate up the right-hand side, knowing the initial velocity, this quantity here, you can then find the final velocity. So that's an alternative way of finding one of the important quantities which we are going to deal with. So next week, we are going to look at several examples, but we want to use this and link it with conservation theorems because it plays an important role in all of physics. So you're going to see this kind of equations, not only in classical mechanics, you will see them in quantum physics, in quantum mechanics, in statistical mechanics, in electromagnetism, and so on. So these are some basic equations in actually physics and the physical analysis of a system. So I wanted just to bring it up because I know that many of you have seen this before, but we are going to start from this one on Monday with some examples, and then we are going to link it with conservation theorems and conservation laws. Any questions so far? Everybody happy? Okay, so what we're going to do now is to switch over to the breakout rooms. And for those of you which are here, we are going